Good evening. Tonight's lesson is going to be over the first lesson in the electricity and magnetism module. I'm going to be covering charge, electric charges, and Coulomb's law. Static electricity. Some part of static electricity means that the charges are stationary. This occurs when charge builds up on an object, usually by two substances running against each other. Electrons are transferred from one object to another. Some examples of static electricity is when you have static hair when you rub a balloon against someone's hair so it sticks up, like you see in the picture of a child going down the slide. An electric charge, it is an attraction or a repulsion between a proton and electron. And there are two types of electric charge. You have a positive, which can be found on a proton, and a negative that can be found on an electron. Atoms are charged by gaining or losing electrons. And remember that larger objects are made up of atoms, so this is also what happens when you feel static electricity. Those atoms in your body are either getting charged by those protons or electrons moving. Ways in which objects can become charged. The first one is charging by friction. These are objects that can be charged by rubbing together. An example, wearing socks in the winter and dragging them across the room while you are walking. You can go up to a person after doing this and shocking them, or sometimes you shock yourself by touching the doorknob. Number two, charging by conduction. These are objects that can be touched to one another object. An example, after you rub your socks, you go over and touch your friend on the couch. You feel a shock. This is happening because that charge is being charged by conduction, by touching another object. Number three, charging by induction. This is when two objects are brought near an uncharged object, but not so that it touches, when the two approach the electron and are either attracted or repelled by the charged object. Grounding. The uncharged object is grounded or touched by a conductor away from the charged object. When this happens, electrons either flow in or out of an object. So when the object is removed, the object has a charge. So there's a lot of different ways that grounding can happen. I'm sure you've probably heard about grounding. When a lightning strikes a building, they have grounding tools that can be used to move the electric charge from the lightning bolt all the way down to the ground, where those electrons can be scattered out and safely dispersed. Here are the charge rules. Two charges with the same sign will repel each other, and two charges with different signs will be attracted to each other. So two positives will repel, same thing as two negatives will repel. But if you have a negative and a positive, they're always attracted to each other. I always remember this by the simple ruling as opposites attract. All right, so now we're going to go and talk about Coulomb's law, or Coulomb's quantized with the different charges. So the charge is a multiple of a minimum value. It is value of the charge on a single electron or proton. Both have the same charge value, but electrons are negative and protons are positive. So if you see the constant E, you have it below. It's 1.602 times 10 to the negative 19th coulombs. Coulomb's law states that the force between charged particles is directly proportional to the charges and inversely proportional to the square of the distance between them. So you have a formula that describes Coulomb's law, and you're going to be discovering this in some of your virtual labs. So here is Coulomb's law and some of those constants that you have to identify with it. So remember that K has a value of 9.00 times 10 to the 9th and converts the ratio to an equality. The charge Q must be in coulombs and R is in meters. So charges are often given in microcoulombs. The force between like charges will point directly away from the other charge, and forces between opposite charges point toward the other charge. Electric fields. The space around a charged particle where it is pushed or pulled with another charge. you have an equation that talks about the electric field, and it's E equals F divided by Q. Field are represented by arrows. Electric field is also a vector, so make sure you have this clear because you must include direction and magnitude when asking about electric fields. However, it is sufficient to say either away from the charge or toward the charge if the value is for a point charge. That would be considered a direction. So here is the practice problem that I want to walk you through. It says a 2.00 microcoulomb charge and a negative 5.00 microcoulomb charge are placed 25.0 millimeters apart so that the 2.00 coulomb charge is to the left of the negative 5.00 charge. So you have to think about the directions and location of these two charges, which is given to us in the problem. So letter A states that you're going to draw the FBD, a free body diagram, for the 2.00 charge. So what you're going to do is you're going to have the positive, again, so the positive, and then all you would have to do is show the direction. And based on what the problem told us, it would be to the right. So now it says draw the FBD for the negative 5 charge. So now since it's on the left, we would have the negative, and then it's going to be attracted to the positive, so the arrow should be pointing that way. And then letter C says, what is the magnitude of the force on the 2 charge? So what we are going to do is plug in the direction, so it's 25.0 millimeters times that constant, and changing it to meters again. That's what the conversion factor is. Remember, it always has to be meters. A lot of students forget this when they do the practice problems. So it should be 0.025 meters. Now we're going to use the Coulomb's law formula. Plug in what we know. This is the constant. This is also the constant of the 2 charges. And then you're going to divide it by the distance, which is what we did up here. Square that, and we should get in our calculator 144 newtons. So what is the magnitude of the force of the negative 5? So now since it's on the left and it's going in the opposite direction or traveling to the left, we have to add that negative sign in front of the force. So that's why we'd have negative 144 newtons. All right, now E says draw the field lines for 2.00 charge. All that's asking is to add this other arrows for that charge. So basically you would draw something like this. Same thing for letter F, draw the field for, that's supposed to be the negative charge. So you do the same thing for the electric field, except now it's going to be the opposite direction. And letter G says, how far apart must the charges be moved to cut the magnitude for the force in half? So now what we're going to do is try and rewrite the formula to change it so where it's half of the force. So we take that 144 that we calculated in letter C, divide it by 2, and we should get 72.0. Then we're going to rewrite the Coulomb's law equation to solve for R and plug in what we know. So we have the 2 constants and the forces of the charge. And remember, and if you're getting confused on why it's written the charges for 2 times 10 to the negative 6, remember that you have to have it in coulombs, so that M here means that you're going to have to convert it to just coulombs. So that's what those conversion factors is. Very similar to what we did for the distance here. Okay, so then the 2 charges, and then now we're going to divide it by 72 because we asked to cut it in half. That's why we divided by 2 at the beginning of this problem. So we plug it into the calculator, we should get 0.035. 0.354 meters. And that is it. So please let me know if you have any questions or comments about this recording. Thanks for watching.